Let's face it, constrained optimization is almost never easy, but there is a general approach that is as powerful as it is simple. Let's look at an example where we start off doing things the traditional way. Find the maxima and minima of the function f of xy equals x minus 2y. Hey, wait a minute, this isn't going to work. This function's too simple. There are no critical points on the plane. So what do? There's no maxima and minima. Oh, wait a minute, there's a constraint, and that constraint is that x squared plus y squared has to be equal to 4. That is, x squared plus y squared minus 4 equals 0. That's a circle, radius 2, centered at the origin. Okay, now we're talking. How are we going to do this? The method that you learned when this was the boundary of a two-dimensional domain was to parametrize it. So let's say, okay, this is going to be easy. We're going to let x of t be 2 cosine t, y of t be 2 sine t. T goes from 0 to 2 pi, right? Just a circle, radius 2, centered at the origin. Now plug that x of t and y of t into the function f. And now we get a function that just depends on t. It's going to be 2 cosine t minus 4 sine t. And now we pretend we're back in single variable calculus. Now it's just a standard max-min problem. What do? We take the derivative, we get minus 2 sine t minus 4 cosine t, set that equal to 0, solve for t. How do we do that? We move the 4 cosine t over to the other side, divide out, got some tangent going on. Okay, so t is going to be arctan of minus 2. You got to be a little careful. Arctangent is going to take two values here, and we're going to get two critical points. A maximum at x equals 2 over root 5, y equals negative 4 over root 5, and a minimum at minus 2 over root 5 and positive 4 over root 5. Okay, that's the traditional way to do it. That's how you would do it if you had something nice like a circle in this case, and that works. But what happens if you can't parameterize that constraint set very easily? Is there a different approach? There is. There's a much more general method. Let's go back to this example and just rethink. Think in a different way. Let's look at level sets. So consider the level sets of this function f. Well, that's x minus 2y equals a constant. That's going to be a straight line. All the level sets fill up the plane with straight lines of slope 1/2. And notice what happens. At those extrema, at those critical points, it certainly appears as though the level sets of f are tangent to the constraint set. That's exactly where these critical points are occurring. Is that always going to work in general? Does that make sense? Well, let's think about it, and let's think to see if we could solve this problem using that idea. Let's think of the constraint x squared plus y squared minus 4 equals 0 as a level set of a function g of x comma y. Now, what do we have? Well, if we look at the gradients of these functions, f and g, we know that gradient vectors are orthogonal to level sets. So the level sets of f are going to be tangent to the level set of g, where g equals 0, exactly where the gradient of f and the gradient of g are parallel. They're not necessarily the same vector. They're not necessarily pointed in the same direction. Maybe they are, maybe they aren't, but they are going to be parallel because the gradients are orthogonal to the level sets. So tangent level sets means parallel gradient vectors between f and g. Okay, now we're going somewhere. Now we can do something. What do? Compute the gradient of f. That's the partial with respect to x and the partial with respect to y. That's 1, negative 2. Simple. Compute the gradient of g. That's partial with respect to x, partial with respect to y. That's simple. 2x and 2y. Now, what does it mean for them to be parallel? What it means is that there's some scalar multiple, that the gradient of f is going to be some scalar multiple times gradient of g. What do we call that? Let's call it lambda for now. We'll see why later. So here's our equations. Gradient of f equals lambda times gradient of g. That encodes this parallelism. This is really two equations. The x-coordinate is 1 equals 2 lambda times x, and the y-coordinate The second equation, minus 2 equals 2 lambda times y. Okay, that's two equations. How many unknowns? Well, 3 unknowns. But we can eliminate that lambda with a bit of algebra. We get y equals negative 2x, and we can plug that into the original constraint equation, x squared plus y squared equals 4. When we do that, we get that 5x squared equals 4. That is, x squared equals plus or minus square root of 4/5. Those are the x-coordinates of our maxima and minima. Solve for the y-coordinates, and boom, we're done. That's a different way to solve this problem.